Hi everyone, and welcome to our module on correlations. Let's imagine you had a data set with a number of patients and you knew how many pack years each patient had smoked. And pack years is the number of packs per day times the number of years someone had smoked. And let's suppose you plotted the pack years of smoking along the x-axis and the number of years each person lived on the y-axis. We can imagine that the more you smoke, the less years you live. So the data set would have some type of downward trajectory like this, so that people who smoked a really long time way out here live fewer years than people who haven't smoked much at all. They would live more years up here. Now, if the only thing that determined lifespan was the number of years you had spent smoking, if nothing else mattered, just the number of years smoking determines how long you live, then the data set would be a perfectly straight line like this. Now, in reality, we know that many things determine lifespan. Smoking is certainly a factor. The more you smoke, the earlier you may die, but many other things also matter as well. So the real data would actually look something like this. There'd be a lot of scatter, although there would be a general downward trend so that the longer you've smoked, the less number of years you lived. And what statisticians do is use mathematics to create a best fit line through scattered data like this. And the line they create looks something like what I'm going to show here. And this line minimizes the difference between the lines in each of the points. If we moved it, say, this way or that way, we would have more distance between the points. This line is mathematically calculated to be the best fit through this scattered data with the least deviations from the line for each data point. And we can characterize this best fit line with something called the correlation coefficient. It's also called the Pearson coefficient. And the characteristics of that line, the correlation coefficient of that line, tells us something about how much smoking impacts lifespan. So the correlation coefficient is a measure of the linear correlation between two variables. In the example we were just discussing, it's the correlation between smoking and lifespan. And the number of the correlation coefficient represents the strength of association between the two variables. It's a number from -1 to +1, and the closer the number is to 1, either positive or -1, the stronger the relationship. We'll talk more about this in a minute. If the correlation coefficient is negative, it means there's an inverse relationship. For example, it would mean more smoking leads to less lifespan. If the correlation coefficient is a positive number, it means there's a positive relationship, so that more smoking means you live longer, which we know is not the case in reality. If the correlation coefficient is 0, it means there's no relationship. And the closer the number is to 0, the weaker the relationship between the variables. So let's look at some graphical examples of the strength of the relationship. So here's a data set over here on the left side of the screen where the R value, and R is the number used for the correlation coefficient, is plus 0.5. So first of all, it's positive, which means the relationship is positive like this. The more of the variable on the x-axis, the more you get of the variable on the y-axis. But the number is 0.5, which is relatively weak. It's far away from 1. So it means that this relationship is not that strong. And you can see that in the data. The best fit line through the data has a lot of scatter around it on both sides. Now let's look over on the right side. Here we've got another positive R value, so there's a positive relationship. But this time the R value is plus 0.9. It's very close to 1. And you can see in the data set that this line almost touches all the data points. These data are neatly lined up close to this line, and that's because there's a very strong relationship between the variable in the x-axis and the variable in the y-axis. So just remember that the closer the correlation coefficient is to 1, either positive 1 or negative 1, the stronger the relationship. And the closer it is to 0, the weaker the relationship. Now here are some graphs showing the direction of the relationship. This relates to whether the correlation coefficient is positive or negative. So here's a chart on the left showing an R value of minus 0.5. So it's negative, so it's an inverse relationship. The more of the x-axis variable, the less of the y-axis variable. And it's a negative 0.5. It's a relatively weak relationship. There's a lot of scatter in the data. In the middle, we've got a positive 0.5, so the data are similarly scattered or about the line, but they're in a positive direction. And then over here on the right, we've got a 0, which is no relationship. And you can see that these data in this chart over here on the right really don't go up or down. They're pretty even across, and that's because there's no correlation between the x-axis variable and the y-axis variable. So many studies will report relationships with a correlation coefficient. For example, imagine there was a study of pneumonia patients and they looked at the white blood cell count on admission and correlated that to the length of stay in the hospital. They might report an R of plus 0.5. What does this mean? It means that the higher the white blood count, that's the x-axis or independent variable, the higher the length of stay, which is the y-axis or dependent variable. And if they showed a chart of that, it would look something like this. It would have the white blood count here on the bottom and the length of stay on the y-axis here, and the relationship would be something like this, a straight line with lots of data points around it, showing you that the R value is positive 0.5. Sometimes the studies will also report a p-value, and so if there's a p-value, if it's less than 0.5, it indicates a significant correlation, and if it's greater than 0.5, it indicates no significant correlation. So this is a statistical test to see if the R value that was found is statistically significant. A related measure to the correlation coefficient is something called the coefficient of determination, and this is the R squared value. So you just take that R number and you square it. And sometimes this is reported instead of the R. So when you square it, you're always going to get a positive number. So we lose that information about whether the relationship is positive or negative. But sometimes this is okay. For example, we know that smoking negatively impacts lifespan, so the positive or minus number is not that important. And when you square it and it goes away, people can still infer the relationship. And the reason authors of clinical studies like to report the R squared is because when you square the R value, the R squared will indicate the percent of variation in Y explained by X. Let me give you an example down here. So let's look at the left side of the screen. So here we've got some data with a line through it, and the R squared value is 0.6. This means that 60% of the variation in the y-axis is explained by X. So if this were smoking down here on the x-axis and this were lifespan, the R squared says 60% of your lifespan is determined by how much you smoke. And that's an easy to understand number, and people like to report numbers like that. And that's why the R squared often gets reported instead of the R. Let's look over here on the right. We've got an R squared of 1, and the data perfectly fall on this nice straight line. This would mean, if we ever saw this in a clinical study, that 100% of the variation in Y were explained by X. So let's go back to our example of the pneumonia study. So if this were the white blood count down here on the x-axis, and this were the length of stay, it would say that 100% of how long you stay in the hospital is determined by your white blood count at admission. Now that's not going to happen in reality, but I'm just giving you an example here. So this is what the R squared is used for, and this is why it's often reported instead of the R. And that concludes our module on correlation.